In November 2023, LIGO's twin detectors felt something impossible. A crash, a split-second scream in the fabric of space-time that lasted barely 10 milliseconds, and packed into it the most massive black hole merger humanity has ever recorded. Two giants, one around 150 times the mass of our Sun, the other nearly 100, colliding in the deep past of the universe and fusing into a single black hole roughly 225 times the Sun's mass. But here's the part that made physicists stop. Everything about how those two objects came to exist seemed to break the rules of stellar evolution. They sat right inside what astronomers call the parent stability mass gap, a forbidden zone where black holes, according to the textbooks, should not be able to form. And on top of that, the signal itself was missing a piece. It started at full volume, like a bell struck by a hammer, when it should have begun as a whisper and swelled into a roar. Something wasn't right. So, earlier this year, a team of researchers proposed something so strange it made headlines. What if what rang out across the cosmos was, in fact, a wormhole, an exotic tunnel through the very structure of the universe? And for the first time in the history of gravitational wave astronomy, the wormhole interpretation came out ahead of the black hole in the statistical showdown. Join me, because we're about to answer the question everyone has been asking since that paper dropped. Have we finally found a real wormhole? We'll break down why this signal doesn't fit, and whether we should be excited. Full disclosure, the answer isn't a clean yes or no, but it might be the most interesting answer in modern physics. Before we get near wormholes, we need to talk about how we heard this signal at all. Everything in the night sky arrives by light, but there's a second messenger, silent to us until recently, gravity itself. Back in 1915, Einstein published his general theory of relativity, which reimagined gravity not as a force, but as the curvature of space-time. Massive objects bend the fabric of the universe, and smaller objects simply follow those curves, the way a marble rolls along the bowl of a trampoline where a bowling ball sits. Fling two black holes into orbit around each other, and they don't circle peacefully. They churn the fabric of space-time, sending out ripples that cascade outward at the speed of light. These are gravitational waves. They carry away energy, the orbit slowly shrinks, and the black holes spiral closer and faster, until in the final fraction of a second, they slam into each other. The signal is so distinctive, it has its own name, a chirp. It starts almost inaudibly, sweeps upward in frequency, hits a sudden violent peak, then rings into silence, the fingerprint of a black hole merger. It has three phases, the inspiral as they wind in on each other, the merger, the moment of collision, and the ring down as the newborn black hole settles like a struck bell into a perfect sphere. How do we catch them? Through lasers. LIGO is two enormous L-shaped tunnels, each arm 4 kilometers long. A laser is split down both arms, bounced off hanging mirrors, and recombined, so carefully that the two beams cancel perfectly. Almost nothing reaches the detector, until a gravitational wave sweeps through. It stretches one arm while compressing the other by far less than the width of a proton, and light suddenly floods the sensor. Essentially a very clever set of rulers, and since 2015, hundreds of cosmic collisions have been stamped on them, most looking exactly like the textbooks said they should. And then came the outliers. Let's bring it back to that November night in 2023, when LIGO and its European partner Virgo picked up an event catalogued as GW231123. Under the standard interpretation, the two colliding black holes had masses around 150 and 93 times the Sun. Their remnant weighed in at roughly 225 solar masses. By far the most violent merger ever detected in a galaxy billions of light years away. But it's the details that should make you suspicious. First, those masses. Stars forge black holes when they die, but in very massive stars, the core gets so hot that radiation converts into pairs of particles and antiparticles, violently destabilizing the star and blowing it apart before it can collapse. So, ordinary stellar evolution should not produce black holes between roughly 65 and 130 solar masses, the parent stability mass gap. And yet here were two black holes sitting precisely where the rulebook says they cannot be. Second, the signal shape. Remember the chirp, the rising, accelerating whoop of two objects spiraling inward? GW231123 barely had one. The signal was extremely short, about 10 milliseconds, with no clean-in spiral in the detector's sensitive band. It was as though we walked into a concert hall halfway through the crescendo, the music slammed in at full volume, and then stopped. The standard explanation said these weren't binary partners. Two loners formed somehow in this forbidden region, crossed paths in a dense cluster, snagged each other, and merged fast. Plausible. But is it the only one? In 2026, a team decided the signal was strange enough to test something far stranger. Here's the thing about black holes. They have an event horizon, a one-way membrane. Nothing that crosses it ever comes back out. The waves we detect from a merger are generated outside the horizon, the in-spiral, the collision, the ring down. After that, the signal should be dead quiet. A black hole is a one-way door, and the music never bounces back. But what if the object in that collision wasn't actually a black hole? Nearly a decade ago, physicist Vitor Cardoso and colleagues pointed out something remarkable. If the object formed by a merger is not a black hole, but something without a horizon, a wormhole, say, the aftermath looks completely different. Gravitational waves wouldn't just ring out and vanish. They would crash against the throat of the wormhole, bounce back, and ring out again, each echo fainter than the last, like sound reverberating off the walls of a vast cave. These are post-merger echoes, the smoking gun astronomers have been listening for, first proposed theoretically in a paper literally titled Echoes from the Abyss. In 2025, a team led by physicist Qi Lai at the University of Chinese Academy of Sciences applied this exact idea to a 2019 oddball signal, GW190521, proposing that what we heard was the echo of a collision ringing through a wormhole connecting our universe to another. The data didn't fully commit. The standard interpretation still fit slightly better. But then this year, the same team turned their wormhole model loose on GW231123, and something shifted. Could this impossible signal be the echo of a collision from another universe ringing through a throat in spacetime? When they compared the two hypotheses head-to-head using the full machinery of Bayesian statistics, the wormhole echo model came out on top. Only slightly, scientists would describe the support as weak to moderate, but on top nonetheless. In a decade of gravitational wave astronomy, a wormhole interpretation has never beaten the standard black hole one in real data. Not once. It happened for the first time in 2026, and it wasn't a fluke. In one event, the more complex their model, the stronger the wormhole case became. So, have we finally found a real wormhole? Before we answer, let's look at what one actually is and why the idea has spent a century being laughed out of the room. Because here's the twist. Even the scientists proposing this add 100 caveats, and those caveats are about to become very clear. The wormhole is almost as old as general relativity. 2 decades after Einstein published his field equations, he and Nathan Rosen discovered that the mathematics of gravity contains something extraordinary. Bridges, solutions to Einstein's equations linking two distant regions of spacetime through a tunnel. These became the Einstein-Rosen bridges, the first theoretical wormholes. You've seen the classic visual, paper with 2 dots far apart, folded so they touch, a pencil pushed through, a shortcut across the whole page. But there was a brutal catch. The maths showed these bridges would be catastrophically unstable, pinching shut within a fraction of a second, crushing anything trying to pass, even light. Einstein-Rosen bridges were less like tunnels, more like doors that slam shut the instant they open. In 1988, Michael Morris and Kip Thorne asked a bolder question: could a wormhole be held open, stable enough to travel through? To keep a wormhole's throat from collapsing under the crushing grip of gravity, you would need to thread its walls with something truly bizarre, a material with negative energy density, exerting negative pressure, pushing outward against the collapse. They called it exotic matter. Now, this isn't Antimatter, that has positive energy. Exotic matter is far weirder. Drop a pebble made of it, and instead of falling, it would accelerate upward, pushed away by the planet instead of pulled toward it, pushing the wormhole's walls apart against the weight of the cosmos. And here's the kicker. Physicists have never observed anything like it. No exotic matter. No macroscopic negative energy. For 35 years, that has been the wormhole's death sentence, an elegant piece of mathematics demanding an ingredient that, as far as we know, doesn't exist. Wormholes live on the far side of science fiction because they need impossible fuel, which is exactly why 2026 might be the most significant year for wormhole physics since Einstein himself. Wormholes without the impossible fuel. Here is where the story turns. In the spring of this year, almost exactly in parallel with the GW231123 announcement, two physicists in Mexico City, Leonel Bixano and Trinity Matos, published a paper in Physical Review DE with a quietly explosive title, The Possibility of the Existence of Wormholes in Nature. The exotic matter problem arises because the wormhole solutions we've known for decades demand negative energy. But those solutions are built on the simplest version of Einstein's gravity, nothing but spacetime itself. Bixano and Matos asked, what if our universe isn't that simple? What if, alongside gravity, there are other fields already predicted by the deeper theories physicists take seriously? They built an exact rotating wormhole solution with two extra ingredients, an electromagnetic field giving the wormhole electric and magnetic charge, and a scalar field called the dilaton, which shows up across modern physics, in string theory, extra dimensions, and early attempts to unify gravity and electromagnetism as a broker between them. And here's the stunning result. When you include these fields, the wormhole works. It satisfies the standard energy conditions, the very checks physicists use to decide whether a solution is physically reasonable. No exotic matter, no negative energy, no impossible fuel. If that holds up, the single biggest objection to wormholes simply evaporates. They become a natural prediction of Einstein's equations, provided the fields the theory predicts actually exist. And since string theory, extra dimensions, and dilaton fields are serious candidates for the deeper laws of the universe, that's a very big provided. The paper even checked whether anything could cross such a wormhole. Near its equator, tidal forces are savage, gradients that would stretch you thinner than spaghetti. Near the poles, they're gentle and finite. The wormhole, the authors found, effectively sorts its visitors. Dive in near the poles and the throat opens into a narrow, passable tunnel. Approach near the equator and you meet a wall of flattened spacetime. Light at the right angle passes clean through, meaning such a wormhole would be not just mathematically real, but traversable. And every black hole we've ever seen, they note, is exactly where you'd hide one. The supermassive things in the hearts of galaxies could, in principle, be wormholes in disguise. At this point, you might wonder, is there any physical reason to believe wormholes are connected to our universe? In the last decade, physicists have come to suspect they may not be an exotic sideshow at all. They might be woven into the very fabric of quantum mechanics. It starts with an idea that sounds like nonsense and refuses to go away. ER equals EPR, named after two landmark papers from 1935. On one side, the Einstein-Rosen bridge, we just met the wormhole. On the other, the Einstein-Podolsky-Rosen paradox, two particles linked so deeply that measuring one instantaneously determines the other, even across a galaxy. Einstein hated this, calling it spooky action at a distance. In 2013, Leonard Susskind and Juan Meldacena tied everything together. What if entanglement and wormholes are the same thing? What if two entangled particles are literally connected by a microscopic bridge through space-time, a wormhole too small to see, but mathematically real? In their picture, entanglement is a wormhole seen from the quantum side. This conjecture, if true, offers a way out of physics' deepest paradox. In the 1970s, Hawking showed black holes slowly evaporate, leaking radiation over incomprehensible timescales. But if that radiation is featureless, everything that ever fell in, every atom, every secret, is destroyed, violating quantum mechanics' most sacred rule. Information can never be lost. ER equals EPR suggests the interior of the black hole stays quantum connected to the outside. Information isn't destroyed. It's recoverable in principle from the radiation itself. Then in 2022, scientists at Caltech and Harvard built a holographic wormhole, not in space, but on a quantum computer. Using Google's Sycamore processor, they engineered two entangled systems that, by the mathematics of ER equals EPR, should be connected by a wormhole. They injected a quantum bit into one side, applied operations equivalent to threading the wormhole with negative energy, and watched. The information emerged on the other side, refocused onto its entangled partner. Information had passed through a quantum tunnel. Physicists urged caution. The lab system was vastly simpler than a real black hole, and nobody claims literal spacetime geometry on a chip. But the point stands, wormhole-like physics is no longer just mathematics, it's demonstrable on demand in a lab. So now we have the pieces. A gravitational wave signal that refuses to look like a black hole merger. A hypothesis that impossible objects like wormholes would sing with post-merger echoes. A 2026 statistical analysis that, for the first time ever, lets the wormhole beat the black hole in real data. And new physics saying wormholes don't need exotic matter, and might be hiding in plain sight inside the very objects we call black holes. Now, for the honest part, here's where we separate science from headlines. Could GW231123 really be the echo of a collision in another universe, ringing through a wormhole throat into ours? The authors model what the echo of a wormhole-born collision would look like, a single isolated pulse, since the wormhole would collapse or later echoes be too faint, and compare it against the standard merger explanation using the same Hanford and Livingston detector data. The wormhole model recovered the signal just as well as the standard near-identical signal-to-noise ratios. Push the statistics to decide which story the data prefers, and the wormhole interpretation comes out ahead only slightly, weak to moderate support in the language of Bayesian model comparison. Real, but not overwhelming. And the scientists themselves note their echo model is still a simplification, a single dominant pulse, nothing on complications like spin, which could shift the verdict either way. So, the honest answer to our question, have we finally found a real wormhole? Is not yet. Not even close. A weak statistical preference in a single 10-millisecond signal is a long way from a discovery. The physics community will not be convinced by one event, and neither should you. Astronomers have been burned before by anomalous signals that turned out to be dust in the data. But here's what should excite you. This is the first time in gravitational wave history that a wormhole interpretation has ever beaten the standard one in a head-to-head comparison. It happened in an event whose properties, the forbidden masses, the missing chirp, were already screaming that something unusual was going on. And it happened in the same year that a separate, peer-reviewed paper offered a mathematically consistent way for wormholes to exist without relying on undiscovered exotic matter. 3 independent lines of evidence, the anomalous signal, the new wormhole physics, the growing quantum experiments, have all, in the span of a few months, quietly converged. What happens next? More detections. The catalog is growing fast. This summer alone, scientists added over 160 new signals, bringing the total to nearly 400, and future detectors like the Einstein telescope promise to see 10 times more, and hear fainter echoes than anything we can today. With every new short, shapeless, impossible signal, the wormhole hypothesis gets another chance to prove itself or to be ruled out for good. And here's the wonderful part, you now know what to listen for. A black hole merger has a chirp, a crescendo, and silence. A wormhole colliding with a black hole would ring, and then echo like a drumbeat in a cathedral. One day, with better instruments, better models, and a little patience, we will know the answer. Either the echoes keep coming, steady and unmistakable, and the universe turns out to be filled with tunnels we never knew existed. Or the next generation of detectors sees precisely nothing, and wormholes return to the footnotes, a beautiful mathematical mirage. Either way, science wins. Either way, we get closer to knowing what kind of universe we live in. For now, the short answer is no. We have not finally found a real wormhole. But for the first time in a century, the question is no longer just mathematics. It's an experiment. And experiments eventually always answer. If you enjoyed this one, hit like, subscribe, and ring the bell, because the moment that first unambiguous echo appears in the data, you'll want to hear it here first. Thanks for watching, and I'll see you out there among the stars.